The Stern-Gerlach experiment produces results that are direct evidence of the laws of quantum mechanics in action. In this video, you will learn how Stern-Gerlach experiment reveals that the electron possesses spin. It is the fact that electrons possess a magnetic moment which makes it possible to perform experiments involving the intrinsically quantum properties of spin. This is the experimental arrangement of the Stern-Gerlach apparatus. A collimated beam of silver atoms is heading in y direction, passing through an inhomogeneous magnetic field directed in the z direction. Since the silver atoms possess a non-zero magnetic moment μ due to a single 5s electron, the non-uniformity of the magnetic field will cause the atoms to experience a sideways force Fz, where U is the potential energy of the silver atom in the field. Thus, we obtain a force experienced by atoms as following. In classical expectation, the magnetic dipole moment vectors of atoms should form a continuous spread ranging from -μz to μz, causing a line on the observation screen along z direction. However, experimental results show that silver atoms arrive on the screen at only 2 points, which correspond to magnetic moments of ±μp, which is known as Bohr magneton. Therefore, we observe only 2 allowed values of spin, equal to ±1/2. Now, let's take a look on repeated spin measurements. Can we determine various components of atomic spin simultaneously? Consider a series of spin measurements using a sequence of Stern-Gerlach devices. In this experiment, atoms are separated in the first device according to their z component of spin. Those with spin up are then passed through a second device in which atoms are separated according to their x component of spin. Those with spin up are passed through a third device, which separates the atoms according to their z component once again. The simple expectation is that, since these atoms have already been preselected to have spin up, they will all emerge from the final device in the spin-up beam. It turns out, however, that this is not what is observed. The atoms emerge randomly in either beam, but with equal probability. This example shows how only one component can be known exactly at any one time. Quantum effects prevent the simultaneous exact measurement of both the x and the z components of spin, meaning that measurement of the x component will randomize the previously exactly known value of z component. And when we try to measure z component of spin, we learn nothing about the x component. Therefore, it appears that it is not possible to measure both components of the particle spin precisely. We notice that there is much in common between the double-slit experiment and the Stern-Gerlach experiment. In the case of the two-slit experiment, wave-like interference pattern appears only if we do not observe the particles, and when we start observing which slit a particle passes through, pattern indicates particle-like behavior. This once again proves the law of quantum mechanics. It is impossible, even in principle, to have complete knowledge of all the physical variables that characterize the state of a system. In conclusion, the Stern-Gerlach experiment proves that electrons possess spin which is quantized, and that under no circumstances is it possible to have exact knowledge of more than one component of the spin of a particle. In fact, the original experiment, first performed in 1922, had nothing to do with the discovery of electron spin, since the existence of spin was not even suspected at that time. It was only later been used to illustrate the fact that electrons possess spin. Thank you for watching this video and stay safe. Bye!